I'll get the recording going so I can welcome everyone officially to our second to last Thursday together. Yeah.
You don't, no class next Thursday?
No, second to last
Oh,
Thursday.
I'm sorry.
One more week. That's right. Today is Thursday. There's one more week of classes.
The penultimate.
Yes, penultimate. That's a nice GRE word. Well, it is. All right. We were talking about path models. That's what we're doing, right?
Mhm.
And I believe I sent you an email yesterday letting you know that the last bridge activity is available due Monday night. You should be able to answer most of it. Vladimir is going to lead it as usual. We're good on that. And your path model, last homework, is open, due 2 weeks from today.
Oh,
Thursday
yes,
of
we did
finals
that.
week. Yep. So let us know if you need help with that. I'm not going to ask if anyone has any questions yet. I'm not that
I
delusional.
haven't even
But
opened
yeah, it's fine. Just I know some folks want to get things done, and some folks want to like space it out as long as possible so they can get other things done. So I just want to give you the flexibility to get it done when you want. That's all.
Thank you.
So you want to work ahead to get it done early? Be my guest. But this is the kind of thing that you're going to be working on, path models. So what are path models for? Let's start there. Why am I showing this to you?
If you have a variable and it is both a predictor and an outcome,
Mm-hmm.
it has to be in a path model.
Yes.
You can't do it in your variance software.
If you want to fit a model in which a single variable is both a predictor and an outcome, so let me put up, like this bottom picture right here is a good example of that. This is slide 8. So y1 is an outcome with respect to x1 and x2, but it is a predictor with respect to y2. And yes, you can fit separate regressions, like I'll predict this one from these things and this one from these things, and then try to stitch it all back together again. But that is a limited approach that will not allow you the flexibility to add additional things to the story. So that approach has somewhat fallen out of favor. And in fact, example 6A that we're going to maybe start talking about today, maybe not, we'll find out. That actually was during my Nebraska days, a colleague got feedback on a manuscript that had done the piecemeal, like this regression and this regression and this regression and this regression, and the reviewers were like, "Oh my God, just make it a path model. I can't keep track of 17 different regressions." And she's like, "I don't know how to do a path model." I'm like, "Oh, it's fine." So I taught her very quickly. She learned very quickly, and she's doing path models now. So that's a true story. So we got an extra, and I asked, "Can I use your data to make a class example?" And she said, "Sure." So that's what we're going to do. It's about mindfulness and various things. But yeah, that's one reason. That situation happens in examining something called mediation, which is a term you may have heard before. We haven't talked about in this class. Mediation and moderation are two different things, by the way. They are not synonyms. We have done moderation so far because that's interaction terms, when the effect of one predictor depends on the level of another predictor. Mediation is the idea that, like in this picture, x1 causes y1, which then in turn causes y2. And so then the question is, how related is x1 with y2 after controlling for this intermediate sort of pathway? That's the type of mediation question that these models are very good at answering. So multivariate analysis, broadly construed, especially when one variable is going to be both a predictor and an outcome. What do boxes mean?
Observable constructs.
Observed and measured, a column in your data set. Yep. What do circles mean? Latent, or unobserved, or pretend. Take your pick. They don't exist. You're making them exist through the model.
An error is observed. So
Uh,
why is error not scored?
Not necessarily, because you don't know how much error you have until you fit the model. So you can output residuals and save them to a data set, but the model is the logical prerequisite to knowing what the residuals would be. So in that sense, they're considered latent.
So you're saying that they're estimated rather than observed. Would that be a better way to say
Yeah.
it rather than
Yeah, it's something the model finds as part of its process. That's what I would say. Go ahead.
So we need to get the error, we need to run the model first. That's why it comes after
Yeah, we don't observe it ahead of time. That's a good way to put it. Yep. What do one-way arrows mean? A slope? Yep. Give me 2 more synonyms.
No.
Fixed slope, that's not it's under the same category. Path, like path modeling, like this is considered a path.
Unidirectional?
Direct effect.
Direct effect.
Yep, because the opposite is indirect effect. That's within the context of mediation. So yes, one-headed arrows are directional relations, slopes as we've been calling them. Two-headed arrows then are undirected associations, covariances. So a covariance is in the units of the variables that it's between, so it's hard to interpret the number, but the direction makes sense. So a positive covariance means higher on x is higher on y, negative would be the opposite. That's the disco dance. Negative is disco. Positive is raise the roof. How's that? Everything has a dance to it today. I'm trying. I'm on caffeine again. Not that you can tell. Yeah. What's exogenous mean?
Predictors?
Yeah, it's a predictor. What's endogenous mean? It's coming in, it's an outcome. Yeah, so there's a variable predicting into it, endogenous. Are you going to hear me use these words?
No.
Nope. Predictors and outcomes. We don't need new vocabulary, but in the world of path modeling, you will see this. We started talking about fit, degrees of freedom, and more vocabulary that goes with that. How about we review that? Would that work? Okay. So I'm starting again on slide 13 for this. So model identification in the context of path models means that the model is estimable. Like you've set it up in a way that it is possible to find the solution. It's a bigger deal with respect to SEM, so latent variables for measurement, for instance. There's a whole lot more that goes into it, but I can skip that part for now. Total degrees of freedom then. This is the number of possible parameters that you can put in your path model. And it comes from this formula, cough, cough, bridge question. V is the number of variables. V plus 1 then in parenthesis divided by 2. This much of it gives you the total number of variances and covariances among those variables. Plus V then adds in the number of means. So every variable has a mean, every variable has a variance, every pair of variables has a covariance. And this is how you can figure out how many those are. So that's total. How many you spend, estimate, is then subtracted from that, and what's left is the degrees of freedom from the model. And that means how many more parameters could you have added?
Sorry, can I ask you to run back over that again? So
Yeah.
the V times V plus 1 divided by 2 is the total number of variances and covariances in the model.
Yeah, so this part of it is variances and covariances. The next plus V again is the number of means, because there's one per variable. Yep. So means, variances, and covariances are essentially the data points that we're keeping track of how many we have. So here's an example with 4. There's 14 total. The question then is, how many do I need to fit my model? How many am I going to spend? And you can think of this like points or money. And how much, if I have 14 degrees of freedom, how many can I spend? 14.
Go
What-
15.
Yeah. What happens if I spend 14 and I had 14, so there's 0 left over? What is the word for that?
Full?
I'll take saturated.
Okay.
There's another one though. Just identified. Yep. Just identified, meaning you just got there, but don't try anymore.
Mhm.
Just this much.
And that's the one that you recommend that we work with.
That's the one that I would recommend for most path models, because then you know model fit is perfect. There's no question that your model has recreated the relationships between your variables because you put in every possible relationship that there is. Then you can focus on how strong those relationships are and what they mean. What if I have 14 total degrees of freedom and I try to spend 15? What's that called? It's either over or under identified. Which is it?
I think it's under, because I remember it being like backwards.
Yeah, it's logically backwards. It's under. I know. Just
Why, 'cause you
go with
don't-
your instinct and then reverse it, and that's how we name things in
Under
statistics.
just means you do not have enough to do what you want to do.
Yep.
Thinking about under.
You're underwater.
Yes.
So what? Okay. I'm trying to do this without that. Here's the vocabulary, slide 16. So just identified is when you spend
Mhm.
all your degrees of freedom. That means that every pair of variables has some kind of specific relationship between them, either a covariance or a directed path slope. Under-identified would be when you're trying to spend more than you have. So under-identified is like being overdrawn on your bank account. And that's what makes the wording confusing. Underwater, like you can't have more parameters than you have pieces of data to estimate them with.
So the thing that is under
Under's bad.
is the degrees of freedom or the number of parameters?
What happens is that you have estimated more than the total possible. So your degrees of freedom would be negative for the model.
So the
The model itself would be considered under-identified because it won't be estimable, because you're trying to do too much relative to what is possible. And that will not happen often in path models unless you make a mistake, essentially, in your code. Like, I can't think of situations in which that would be a problem.
That'd be hard.
It's a much bigger problem in the world of measurement modeling, though,
Because you're measuring latent variables.
if you're measuring latent variables. So if you try to measure a latent variable with 2 items, that's under-identified. That is not solvable without additional constraints. 3 items, by the way, is just identified, and 4 is over. So you can learn that later on. So over-identified means that you have not spent everything. Some of the relationships directly between 2 variables have been overlooked. And that means model fit is not guaranteed to be good, but we have to pay attention to it. That's what that means. So we had some examples. Over-identified is the first one here because there's no direct relationship between x1 and y2 in either of these pictures. So we're assuming that what is here adequately recreates the relationship between x1 and y2 indirectly. And the rules of path analysis, which we'll see more of today, is that we multiply these 2 slopes together, and that creates the expected relationship. Yes?
So will over-identified models be or SAS or student?
Over-identified, yes, because that means you have degrees of freedom left, you haven't spent everything.
Under.
Under-identified will not.
Will not.
Yeah, then you will know that because you will get an angry error message, probably in red text,
In R.
and it will have some kind of words like may not be identified, or not positive definite, or other kinds of things. And in your output, where there would normally be an estimate column, standard errors, p-values, you will just have a column of estimates, because they're not estimates. It's like when it finished iterating, however many, like there's a ceiling on how many times it will try, and it just prints what it had when it stopped. So it didn't converge, it's not finished, it's just decided it was done. Yeah, so if we talk about standardized effects in the correlation metric, so these would be correlations in a correlation metric instead. This correlation times that one is supposed to be what the actual relationship between x1 and y2 is. So it's creating an implied relationship. The question is does it do a good enough job? And if not, then we might want to have that direct relationship to kind of fill in the gaps of where it missed. So long as you have some kind of direct relationship between every pair, your model fit will be perfect and you don't have to worry about it being a bad fit. And then this would be an example of under-identified because there's only one covariance between these 2 variables. There's no way to split it into 2 pieces. It's logically impossible. Okay, here's a better picture. Let's play. And I stole this from someone else's SEM class, so thank you. There's the link below. So these are variables, A, B, C, D, E, and F. Then we have labels for the paths between them. So there are rules to figuring out how these models generate predicted relationships. And they're called Wright's rules. They were developed in like 1938. So this is not new.
Must be the right rule.
So the rules are, no loops, you can't go through the same variable twice, no going forward then backward, and only one curved arrow is allowed from the first to last. So let me give you some examples here. B to D. Okay, so here's variable B to D. The obvious way that these two are related is the arrow connecting them. So the lowercase b is that much. But that's not the whole story. Yeah, you can go from this B through this covariance up to A and then down to D. That's also how it's being recreated. So that's why I have B plus F times A, because F is this covariance and A is this slope.
And you said we multiply those when you go through.
Yep. And so the total model implied relationship between B and D is right here.
Can you explain again why you're not adding F and A instead of multiplying instead?
Multiplication is the way that it works because we're going through. And I'm abbreviating this for simplicity. If you wanted to talk about predicted variances and covariances, then the variance of those go with it. So for instance, I'd need the variance of B times B plus F times A in this case. But it's easier if you just think about it as correlations, because then the variance part drops out and the ideas are still the same. So like a wrong example of A to B, let's go to this one here. I can't do A down to D and then back up to B, because that breaks the no going forwards then backwards rule. Common causes, not common outcomes. All I can do is just these two. If I want to go C to D, here's C, there's D. Now it looks like there's nothing connecting them, right?
There's no direct rule.
There's no direct relationship, but there's an indirect one, because I can go from C over to B and then down to D, or I can go from C all the way back to A and then down to D. So there is a model implied relationship between C and D because of the other paths. Yeah.
Question. Because of your paths identified, would you also be allowed to go from C to A to B to D?
C
To
to
A
A.
to B to D?
No, one covariance. You can't go across two. Yep, that's the last rule.
Oh, sorry.
The last one's one that's hardest for me to count.
You can only use one covariance in the chain.
One in the whole thing.
Yeah, to go from one to the other. So he was just asking, like, can I use this covariance and then use this one to come back down? You can't do that. So here's the good news, folks. You don't have to memorize these rules or figure this out. This is a piece of output you can request that says, what does the model say my correlation matrix should look like according to these rules? And then the question is, what does it really look like in my data? And how discrepant are they? That's the basis of model fit. So this model could fit badly if the way that C and D relate is not adequately captured by these things. And in which case we'd want to connect them directly to repair whatever misprediction we have in the extent of that correlation.
Could you also choose to like break a relationship, like from B to D, if you thought that would be helpful?
To break it?
Yeah, if you got rid of B, could you choose that? I'm not saying that you want to, but
Mhm.
could you?
Yeah, so if this were non-significant, you could remove it and take that degree of freedom back. Let's see, C to D wrong, we can't do this way. We can't go all the way down to E and then back again.
Mm-hmm.
That breaks the rules. A to E. Well, that's a lot of them. I can go through D, that's one. I can go over to B and then through D, or I can go over to C and then to E.
Wonderful variance.
Yeah. So there's quite a few paths that are not in this picture that could be. And that's how we can compute model degrees of freedom. A more direct way is how many things did we leave out? In particular, only one thing is connected to F. All A, B, C, and D are not connected to F directly, so there's those paths. E is not connected directly to either A or B. D is not connected to C. So if we start adding those up, that would be our degrees of freedom, is how many things did we omit?
Okay, you took me out because I'm seeing the slide between A and F and E's in the middle. So can you really break them down?
So what I was saying is like A could have an arrow going all the way over to E directly, or all the way over to F directly. And right now we're saying the only way that A relates to E is indirectly through these other paths. because there's no direct relationship.
Covariance has been established.
And this is how the expected correlations would be built from this model. The short answer is if two variables are not connected somehow directly, there's a chance that their relationship could be wrong. If they are connected directly, they're going to be fine. Unless the rest of the model is really, really wrong. But that's why I prefer for path models to be just identified. Put in everything, because then you don't have to worry about what you're leaving out affecting other stuff. And you can just focus on what's significant and how big the effect sizes are. Fun, right? It gets a little worse. Here's a covariance version. So I made a simpler model. So let's say that I have x1 and x2 I'm bringing into the likelihood by pretending they're outcomes so they can have missing data. And then I'm having them each predict y1, which in turn predicts y2. Okay, so x1 and x2 then are essentially having empty models. That's how you trick them into being outcomes, is you tell the software that they're predictors, and so you want to estimate their mean, which is beta 0, and their variance, which would be the variance of each of their e's. And then those have to get found as model parameters. Then you can have missing data. I'm also including then a covariance between them because they're being considered outcomes. So I'm not saying one predicts the other, I'm just saying they're related. y1 is predicted by a fixed intercept, the slope of x1 and the slope of x2 and a residual. y2 is predicted by a fixed intercept, the slope of y1 and some kind of residual. Okay, so in this model with 4 outcomes, we have 6 covariances that we would want to be trying to recreate. 4 of them are going to be perfect. First off, the relationship between x1 and x2 is directly captured here. That one's going to be fine. The covariance between x1 and y1, right here, is in 2 different parts, but it will also be fine because I have the variance of x1 to get to here, plus I can go through the covariance and pick up this slope as well. So that one's going to be fine. x2 and y1, also fine because the same reason. And y1 and y2, fine because they have a connector. So which ones are not fine? We'll get to those in just a minute. Here's the model implied variances. They're complicated, but they're going to be perfect because each of these has residual variance that's being estimated, and that number will fill in whatever gap remains between what is predicted and what the original variable had for its variance. It just like plugs the hole. So y2, for instance, is going to have some predicted variance based on the fixed effects in red. The E variance that is estimated will then bring it up to whatever the total variance was for that variable to begin with. So as long as each variable has a separately estimated residual variance, that will be the case and it will be fine. The rule is when trying to come up with the variance of a sum is that it's the variance of the stuff inside plus twice the covariance. That's a math thing. So I worked through this. It's very tedious. You're never going to need to do this, but for those of you who think this way, knock yourselves out. So here's the ones that will be wrong. The covariance between x1 and y2 and x2 and y2, because they don't have anything connecting them directly. So their relationship has to be recreated by the things that are in the model otherwise.
Is that a research decision not to create that loop over and under?
Yes, it is.
Okay.
So how you connect these things or not is up to you. And there's no mathematical way to say what's right in terms of direction of things. Like there are many, many kinds of equivalent models if you switch the arrows around. There's only one situation in which I could confidently say to reviewer 2 that I had the order right. I did a study in which I had an outcome that was collected 5 years later. Pretty sure the past does not come second. So the thing measured 5 years later is at the end of the arrow. Like I will die on that hill. But other than that, it's sometimes difficult to defend your choices. But yes, this is your theoretical viewpoint. You can see how well it fits and then try to look for where the misfit is happening, which correlations are not being well recreated. And then you got to add something in that will fill in that hole. All right, a fit then. I'm going to walk through these relatively quickly because you're going to see this again at some point. But most of the fit statistics that you get are trying to ascertain how well you have recreated the patterns in your data with your slopes and covariances. So the target here is a matrix of correlations. That's what fit refers to. And the best option is what's known as a saturated model, or an unstructured model is the term I use for this when I teach longitudinal, and it will be labeled as the H1 model in your output. This is the right answer. It's what if you put in every possible path that you can. That is going to perfectly recreate the means, variances, and covariances. So then the question is, how tall is your best possible model? That's a log likelihood. And then we test against it, like how much worse we are than perfect. That's the logic. So that's one point of comparison. That's the most important one. Another one that you'll see is the worst possible model, in which every variable gets its own mean and variance, but all the covariances are forced to zero. And so then some fit statistics are like, how much better than the worst model did you do? Which is a different way of looking at the same question. How much worse are you than perfect, or how much better are you than the worst? Somewhere in the middle. So global fit then is the question of, did we recreate the patterns in the data adequately enough? Then we have other steps here. So you will get a significance test, which is a likelihood ratio test. You're familiar with these, right? Mm-hmm. So the question is, how tall is the best possible model? That's my saturated. How tall is mine? Mm-hmm. And is it close enough? So is it worse than perfect is the answer. And because it's phrased that way, a significant result is bad, because it means you're worse than perfect. Your model made your data shorter. So this is a switch in thinking about it that takes people by surprise. I could see some of your faces. You're like, what? Significance is bad when it comes to fit. You are assessing how much worse your model is than perfect. So if it's significantly worse, you didn't do a good job.
It's like your normality test.
Yeah, I think you can.
Your other normality test, you want to be non-significantly different from normal.
Yeah, the null means that you used fewer degrees of freedom than everything possible, but you recreated the patterns well enough. That's what you want. If you use all the degrees of freedom, you will recreate the patterns perfectly, and you don't have to worry about it. That's just identified. So this is often disregarded, this hypothesis test of fit, because it's influenced heavily by sample size. So people have made workarounds, different kinds of fit indices that they like better. Yeah.
When we're testing fit, should we test fit just for the empty model? Or do we have to do this for every time we add a predictor?
Ah, okay. Fit in this case is not going to change if you add a predictor. If you add a predictor and turn it into an outcome, however, then you cannot test fit of that because you've changed the dimensions of the correlation matrix that's using to assess fit. So let me back up. General linear models, regression. Mm-hmm. If you had it from me, you never heard the word fit in that class. Do you know why? Because a regression model fits perfectly. That means I have perfectly recreated the mean and the variance of my single outcome. Every regression model will do that, because your fixed effects build some kind of conditional mean, and your variance left over will plug the hole between whatever variance is explained and variance unexplained. So fit is perfect in univariate regression. Now if I have two outcomes, now I have two means, two variances, and covariance. Odds are good that fit will still be perfect so long as I put that covariance in, but then the more you get, the more you got to worry about it. Yeah. So it's a different way of thinking about it, because when we put in new predictors, the question we're trying to answer is, to what extent do they predict this outcome? Is my prediction improved by adding this new piece of predictive information? That is a separate question than did it help the fit. Because you can have a well-fitting model with no significant relationships, because that means it perfectly recreated the non-relationships in your data. That's what it means. There's a whole lot of research on fit indices and how they work. And it used to be the case that everyone agreed on certain values as this is good and this is bad. And that went out the window like 10 years ago or so. So this is a whole big area of research. If you're interested, I can give you some papers to read. But here's just a brief tour of some of these. They all have acronyms, of course, SRMR. Here's a pro tip. If it has the word residual in the name of the fit index, you want it to be as small as possible. If it has the word fit in it, you want it to be as big as possible. So they go in different directions. This has an ugly formula to it, but what it essentially does is tell you how far off on average your correlations are. And less than 0.08 or so is considered acceptable under old definitions. RMSEA is another one that has error or residual in it, so we want this to be small. This is how wrong you are scaled per model degree of freedom left. So this one likes it if you can drop stuff that's non-significant because you pick back up those degrees of freedom. It favors parsimony. And this one has a lot of labels as to what good enough is. Closer to 0 is what you want. Then we get into the fit ones. These are relative to the null model with no relationships, and we want them to be as big as possible, close to 1, above 0.9 or 0.95-ish on those ones. So we'll see those in our example. So the idea here is that you fit your model based on your theory, your questions, however you want to set it up. If you have degrees of freedom left over, then you got to worry about fit. If it doesn't fit well, though, you have to fix it. It's not like you're done. You don't just take your ball and go home. It didn't fit. I'm wrong. You figure out why it didn't fit. Question?
It seems like the degrees of freedom is a researcher choice, meaning if I never bring it in, I can justify my degrees of freedom. But if I have data that has additional data points in them, then I'll maybe open it up to under justification.
I'm not sure I'm following it. So researcher degrees of freedom is a separate idea, by the way. That is a term. No, it's a real thing. It's a term for the sequence of decisions that researchers make that could potentially lead to a good outcome or a bad outcome.
Yeah, I also like that.
Okay, I didn't think so, but that's where my brain went. Okay, so tell me what you meant by that.
It seems like the degrees of freedom is like the number of variables, right?
Yes, degrees of freedom in this context is based on the number of variables you have.
Correct. So if I don't, if I have to explain or not explain more or less number of variables, then I essentially have set myself up for success or justified.
The more variables you have, the more complex your model can be, and the likely more degrees of freedom you will have once you start leaving stuff out. But yeah, if you only have like 3 variables, it's going to be you're not going to have that be over-identified very much, because you'd probably miss a lot of the story. But if you have 10, maybe not all 10 need a direct relationship between them. Yeah, it's up to you. All right, so yes, here's a study that's been cited over 100,000 times where the cutoffs came from, but this study only examined a limited number of things. And so there's been a lot of research since then saying, hey, what about this? What about this? What about this? And what about that? All right, so then we got to figure out why the model doesn't fit if that's the case. What are we missing? And there's various ways to examine this. Local misfit is the term that's used for this. There is an option called residual in all 3 of the packages, so M+, Lavaan, and Stata, and it provides essentially deviations between what the data say the correlation should be between 2 variables and what your model says it should be. And then it rescales those deviations into something akin to a z-score. So the direction is important to pay attention to, because if you have a positive residual, then the outcomes in the data are more related than what you predicted. So you're under-predicting if you have a positive residual. The opposite is true if you have a negative residual. They're less related than what you predict. So we want to look for the largest ones of these and try to figure out how to change the model to accommodate those missing relationships or mispredicted relationships. And there is a way that the software will do this for you. They're called modification indices. The analogy that I use for this is like a cheat code. When my little brother got his first Nintendo, circa 1990 or so, he would buy magazines that would tell you how to beat the game and where all the secret stuff was inside the game. And that was a good investment because then he could beat the game. So I think of these as like the cheat codes, like, oh, here's where the mushroom's hidden. You know, you got to bounce on this thing or whatever. It was Mario, of course. These are score tests, is what they would be called in a stats environment. They essentially say, hey kid, if you put this in your model, here's how much taller your data is going to be. Trust me. And then you're like, but does that make sense? Don't ask questions. I'm just trying to help you here. So it's a combination of looking at what's missing and then what theoretically would make sense to change to address that misfit. And that's art and science. The problem with these, though, is that they will never suggest a different kind of model. They will only give you Band-Aids to repair the one that you have. And this is a bigger issue in latent variable measurement models than in path analysis, though. So, reviewing the steps then, absolute fit, we want that to be good. Figure out why it's not good if we can, and then revise the model until it fits. We have to have decent fit before we can make sense of the results. But then we're not done. So this is the slide that I pulled up last time to answer the question about prediction versus fit. A good fitting model does not necessarily mean it's a good model. It is entirely possible to have tiny, tiny little relationships estimated that are non-significant, and yet, nevertheless, it fits well. So this is effect size, what we're talking about here. In this example, we would have good fit potentially, but no significant paths. So prediction and effect size are just as important as they ever were. All right. For generalized outcomes, we run into software limitations. So I have some notes about what this means in here. I think it would be good, before we dive into that, because we're not talking about that, to revisit our analysis and start looking at a first path model. Would you like to do that? A real example with numbers? The family data we've been playing with?
Sure.
Sure, why not, right? We're here. I have, let's see. We finished part 1 last time. We found out that dad's education predicts dad's attitudes, but not the other people's. And I thought that was going to be my final model, model 3 here. Checked the distribution fit, seemed not great, but not terrible. So here are then part 2, starting on page 11. And I've got examples in here in Stata. I've got examples in here in, I think, do I have Lavon in this one too? Yep, there's Lavon and M+. So 3 different packages. Not even a personal best. I have one handout that had 4. Adding K-list. But all right, here we go. So first things first, we have a different data structure in path analysis than we had to use mixed in or GLS. We're back to wide data. So this means 1 row per sampling unit, and all outcomes are stored in separate columns. They're not all stacked into one column with switches. Yeah.
Transposed.
So what we started with wide data and then transposed it by family. Now we're undoing that. We're back to the original data set. So each outcome is in a separate data column. Yep. So I had used a data set in Stata. Here's an example of how you can create a data set to be used in M+, because M+ does not take variable names. And it only takes text data. Seriously. So CSV or DAT is the format you would need to use in that. So I am using a command I found very convenient in Stata to replace all missing data with -999. That way I don't have blanks or dots that can cause problems in importing the data into M+. And then I used an export command to generate a CSV file, comma, separated values, without labels or variable names, because that actually goes into the code instead. Here's R syntax to do the same thing if you need to make an M+ data set. So I wanted you to have an example of that. Here's the model. Okay, we'll start with Stata. So we're using the wide data. Welcome to SEM. That's how we do path models. There's also a GSEM, that's a generalized version. Yeah,
This fall, maybe.
yeah, maybe.
One step at a time.
What's what?
One step at a time.
One step at a time, that's right. SEM does not have link functions in it. So GSEM came later, and it does multi-level stuff and generalized stuff with link functions, but straight up SEM does not. So, Stata users, 3 lines. Like this is a line continuer and a comment. 2 is only a comment. So this entire thing right here is 1 line, according to Stata. It's 1 command. These things are arrows. And you can write them pointing left or pointing right. I'm doing it to be consistent with how it's expressed in other packages. So this first line here is saying I would like a fixed intercept for all 3 of my outcomes. And note that I'm not having 1 column called marital, I have 3 columns now. So we're back to the original form of the data. I'm then having 2 predictors of the kid's marital attitude, their gender, and then their own education. 1 predictor of mom's attitudes from her education, and then dad's education predicts all 3. So this functionally is 3 regression models at the same time. Separately but simultaneously. So this is analogous to the DV-specific intercept version that we were looking at before, because each column gets its own stuff. Question?
Thinking,
Thinking? Okay.
just compartmentalizing, sorry.
No problem. I'm asking then for E variances. So some of this is default, some of this is not default. Covariances, you can write like this. So I'm allowing the 3 outcomes from the same family to all covary, 2-headed arrows right here. And that's my model. So my approach to writing code, particularly in SEM and path analysis, is to write out everything. I don't want to have to remember what the defaults are and hope that it's the right thing I wanted. So I write everything out. In practice, the only things that you would have to write out would be covariances you're adding and slopes. You get intercepts, you get variances by default.
Does this help control your order of output then, or no?
I don't think it does,
Okay.
if I remember correctly. Like each program reorders it to have
Right,
like the
right,
slopes first, the covariance is second, the variance is third, like,
Okay.
yep.
Right.
Yeah, the commands though, like this comma is super important.
Separates
I know, like do not forget the comma. Things will go badly. But that translates from the slope portion of the model into the variances and covariances portion of the model. MLMV is an option for full information maximum likelihood. What that's going to do is allow missing data on any of these variables. So this approach treats everything as an outcome if you ask for full information. You don't have to worry about putting it that way. I did some linear combinations to show you how that would work. You have to figure out internally what Stata has named each of your slopes. The way that you can do that is an option called CoF Legend, and I think I have that somewhere in here. Yeah, somewhere in here I have that. Then I start asking for a bunch of stuff. Yep, right here. So CoF Legend spits out the labels that go with everything in your model. That way you can refer back to them to do math. So for instance, this one is asking whether the effect of dad's education on the kid outcome and the mom outcome is different. So it's this slope minus that one. Analogous to the -1, thing that we've done before. Standardized output I'm asking for, so I can get slopes in a correlation metric and correlations instead of covariances. S.gof. GOF stands for goodness of fit. SStat means anything after, that's called a post-estimation command. So it's like you're asking for extra stuff out of your model. I want all of them. Log likelihood for the model is not actually given by default, so I had to add that. Your homework is going to ask you for this. If you get the right log likelihood, you have the right model. Same rules. It will take longer to that because the path model is more complicated though. Number of parameters is also something it doesn't spit out by default. And then we get into our squares, we get into residuals, and then we get into the modification indices to potentially improve fit. Yeah.
Earlier in the term, you could get the correct log likelihood if you centered incorrectly.
Yes.
Will that happen here also?
Yes.
So you could be off a little bit with your model, unless we don't have to recenter.
So I don't believe there's any centering required in the path model homework because
Okay.
people typically would not do that unless we have interaction terms in path analysis. But
Okay.
if you have your predictors centered incorrectly relative to my instructions, that will not show up in log likelihood because it
Correct.
still generates the same predictions.
Mhm.
Because my choice of constant was arbitrary.
Yeah. No, I get that.
Yeah.
Okay.
Where that would show up is if I asked for the fixed intercept and that's wrong, then you have the wrong definition of what 0 is in at least one of your predictors.
Okay.
Yep.
Thank you.
Yeah, sure. All right, I have a note here that because of the way that it's bringing all the outcomes into the model, the log likelihood doesn't match M+, but otherwise, these are the analogous fixed slopes and mixed. So here's the regression model predicting the kid outcome, its own intercept, the two kid predictors and the dad predictor. Here's the regression model predicting moms, and here's predicting dads.
Are those lowercase letters? In the,
Yes, lowercase, yep. State is picky about that. It's case sensitive. So when I converted the data set into Stata format, it changed all the variable names to be lowercase.
no, I'm saying like, I figured if we look at before the rights rules,
Mhm.
are these the lowercase, these coefficients are lowercase, the norm?
Yeah, like the labels for the paths?
Yeah.
Yeah, so like this would be the slope that's relating the adult child's gender to their outcome.
Okay.
And these numbers will match what we got out of Stata mixed and GLS and R. Yep. So we have coefficient. That is whatever the thing is, intercept or slope. Standard error, we know what that is, the expected inconsistency across samples. Z is our test statistic. P-value, confidence interval, what's after that. And then I wrote, in terms of the equation, what the analog is here. So if we go all the way back to this equation right here, I labeled the slopes in the equation as they show up here. So this isn't so bad, right? This kind of looks like submodels. Remember the ordinal and the nominal? It's organized the same way, but they're just different outcomes. 3 separate outcomes being predicted simultaneously. Then we get into variances and covariances. This is variance left over in my 3 outcomes. These are the covariances I asked for among them, how related the outcomes are. LR test of model versus saturated chi-2,6.
Chi-squared test for likely ratio of the test, yes?
Yep. So let's take this apart. LR test of model versus saturated. Saturated means the perfect model.
Mhm.
That is going to be the tallest the data can do. Every mean, variance, and covariance separate. So this is a likelihood ratio test of the height of my model versus the perfect one. And in parenthesis here, that's my model degrees of freedom. That means I left out 6 things.
And each program is able to determine what saturated was based upon your input.
Exactly. Yep, you don't have to compute that. It does it for you. And so then to your question, Rebecca, about half hour ago or so, you're saying like, if I add another variable in, well then that changes what the height is because then it's a bigger matrix than it was before. So it's not comparable because you've changed like what the maximum height would be. No? If you add in another outcome, it changes the dimensions of the matrix.
I guess what I want to know is, do I need to do all of these fit checks every time I add in a new predictor?
If the predictor is being treated as an outcome and you add it in new, yes, you need to recheck everything. If it is a truly exogenous predictor that is not in the likelihood, then no. Yes. Predictor that's being treated as a predictor.
It's only a predictor.
Only a predictor. Yes, that's probably the better way to put it. Yeah. So, but you don't have to compute things. We're just looking at things. So like here's the linear combinations. Then I asked for, okay, yeah, so this is CoF Legends output. So do you see how it adds the name for what each of these things is called? That way, if you need to use it in a LINCOM or something, then you know what it is. That's helpful. Standardized solution. So I added this note. That means all variables have been standardized into mean 0, variance 1. And so then we can talk about these as effect sizes. These are standardized slopes.
Z-scores?
The
Or
variables
no?
are essentially z-scores, yes.
Okay.
Yep. So for instance, for every one standard deviation on this variable, this outcome goes up by 0.23. But this is a binary variable, so it's weird to talk about it that way. I know, that frown is exactly right.
I'm just processing right now, sorry.
Yeah. Yeah, for education, for instance, like these are in standard deviations as a unit rather than a year at this point. So it makes them unitless, but it also makes it sort of weird sometimes. But these are the standardized effects. There is no analog to these in mixed or GLS. Then we start getting into the s.goff.
Estimate the goodness effect.
Yeah, so it's going to give you 2 test statistics. And it actually did this labeling. I have a note here. It printed this. And then I have
Is
my
that a
own.
correct label?
Yes, it is.
Okay.
So the first one here is model versus saturated. That's the one we saw up above. So it is technically non-significant. But I'm still going to look at the misfit and see if there's any particular places where it's mismatched, and I want to concentrate on those. So then we have this one. Baseline versus saturated, ignore that. That has nothing to do with your model. That basically tells you whether you have any correlations worth modeling. And
The answer is yes.
yeah, I hope so. Game over. RMSEA is a little high, not super bad, 0.07. We want it to be as close to 0 as possible. Information criteria, you've seen these before. They don't have a reference points. Smaller is better.
No, we have, oh, never mind.
CFI and TLI, these are relative to the worst model, so we want them to be high. We want them to be close to 1, so these are definitely not good enough on that score. SR-MR is okay. I don't know. I've never seen that one in used. The coefficient of determination is what it is, but it's like an overall R-square is what they intend it to be. Then we get into actual R-squares.
I was going to say, you cannot interpret that as a 13%, can you?
I don't know what it really means.
Okay, this is
Yeah,
just-
it's one of those, I'm like, whatever, I'm not looking at that one.
Okay. Fine.
But yeah, look at all the variance we explained. 5% in the kid outcome, less than 1% in the mom outcome, and 7% in the dad outcome. Woohoo! Yeah, this is real data. It's not like in your homework where you have a variance explained of like 80% or something, because I made up all the stuff. And then residuals. Okay, so residuals in this case means offnesses, wrongnesses, deviations. So the first thing it's going to tell us is about the mean. And look, these are all perfect. They're not off at all. That is an expected consequence of the fact that all of these variables have their own fixed intercepts. So that would fill in whatever gap would be needed to get it to the right mean. So that's not going to be a problem. If we do the covariance matrix, so on the diagonal are variances. These are pretty much fine. On the off diagonal are the covariance residuals, how wrong these are relative to the data. And I've highlighted the ones that I wanted to pay attention to. Mom ed and dad marital. That's not in our model. And that's the biggest one by a considerable margin. So that's going to be what's largely driving our misfit, is this relationship wants to be in the data, or it's in the data, but it's not represented adequately in our model. And sure enough, modification indices, cheat codes, it's like, hey, you know what you should do? You should let mom education predict dad marital. So that's what we'll do next.
So could you also use your covariances matrix to say what you may want to take out? Or no?
I wouldn't in that case. I would look at the significance and effect size of the stuff that's in the model, and anything that's low, like close to zero or non-significant, would come out.
Okay.
And then these numbers like would go up a little bit,
Yeah.
but you're saying, it's close enough
Okay.
without that. Yep. So this is what Stata would look like. This is what Lavon looks like. It's very green. It's
Lots
not
of-
easy being green. I'm going to quote Kermit the Frog here. The reason that it is green is because
That's
this,
all comments.
that is, the comments are in there, but this is one piece of a thing that I'm creating as instructions for my model and saving it as an object. So I have syntax 3 is what this is going to be called because it's model 3 in my numbering system, and this is my path model. So the comments start with the # hashtags, and the conventions of how you describe things in Lavon are as follows. Squiggle, squiggle,
Double squiggle.
tilde, tilde, is a variance or a covariance.
Hmm.
And if it's the same variable on both sides, then it's a covariance with itself, which we would call a variance. If it is a different variable on each side, like kid marital and mom marital, that's a residual covariance. So the e's get to be related. It has a weird convention that it allows you to add. That's not addition. That's saying make one for kid marital with this outcome too. It's not really adding.
You just want to add, to do that effect also.
Yeah, like I want a residual covariance for dad with kid and then mom with kid. And then mom with dad is the third one. Squiggle 1 is how you tell it you want an intercept, like a column of ones. And then squiggle anything else is a slope. So y is on the left-hand side, x is on the right-hand side. And that's how I did it in Stata, and that's how it works in M+ as well. A y is on the left-hand side of the squiggle, and x is on the right-hand side. Yeah, and we can't have equal signs because equal signs are used elsewhere, so they had to come up with some other thing.
So when we put this into R, would all these things be on separate lines after the equal?
They don't have to be.
But it makes
So-
it easier to read.
Yeah, it's easier to read. If you want to combine things onto one line, you need a semicolon. And then that shuts one off and starts the next thing.
Okay.
Otherwise, it gets to the end of the line and assumes it's done. Things in here, these are labels. Things in parentheses. I'm using those to do math on. So I am labeling the slope of relating, for instance, dad's education to kid marital as dad ed to K. And then I'd label the other ones so that I could demonstrate how to do linear combinations. So in this case, I have colon equal, which is building a new thing. This is analogous to GLHT. That's what it's doing. But it's doing it through labels rather than places in a series of parentheses with underscores. Like you're used to seeing like spots with zeros and ones. This requires you to actually label the thing you want it to do math on and then have it tell it what math you want to do. So this is a contrast of how big this slope is relative to that one, as labeled by the comments out here. So once you build your whole model inside these quotes, save it as a piece of instruction, essentially, for R, then you feed that into the function for Lavon. So this is a new package. We have not seen this. Latent variable something or another. What does it stand for, Vladimir?
Latent variable analysis.
Latent variable analysis. Yep. There's also a Bayesian version called Blavon with a B in front. So, creativity. So it wants to know your data set. It wants to know what the model is. That's the set of code I just wrote up here. And then what kind of estimation you want. Using robust estimation in this case, and then mimic equals M+ changes to defaults that M+ uses. That should not matter, but I keep it in here just in case. And then what do we want to know? My summary What am I summarizing? This model, once it's fit. Do I want the fit statistics? Do I want the R-squares? Do I want the standardized? Do I want confidence intervals? Yes, give me everything. Why not? Then last but not least, modification indices to check the misfit, sorted. Minimum value of 3.84 is based on what would improve the model significantly for 1 degree of freedom for the chi-square.
Now, is that something that I'm not saying that we now should change, but we could change that to like a 5 if we had justification to make it 5 versus
Yeah.
3.84 versus something else.
Like this is the alpha 05 level. Like if you want to be
Right.
more stringent, then you'd
Mhm.
pick whatever the cutoff is for the alpha level you want.
Okay.
Yep.
So you set that?
Yeah. That's something you can, it'll do it for any value, but that gives you usually a very long list in models that are very complicated. So I'm just saying, just only show me the ones that are going to help. Yeah, and so the full output for R is online. I wanted to also show M+. So M+ did not work the same way as most packages. I don't know if you had a chance to play with it yet. And you don't have to. You can just omit that from your life if you have enough going on. But most packages, like you can write a chunk of code and highlight that chunk of code and run it.
Mm-hmm.
M+ does not work that way. You run your entire file at once.
Oh, like true programming.
Yeah. So you have two choices. Either you have a million separate files, one for each model, one for each thing you want to do, or you stack them all into one, but you comment them out as you turn them off. Like I'll run something and then comment it out, and then the next model comment it out. So you have to be very careful in how you manage your files and the file names. It's very easy to get into what I call file hell.
Model 1, Model 2, Model 3 on the end when you save.
Exactly, yeah. There is a package that Vladimir will help you with, M+ automation. He's gotten very good at that, right?
Yeah,
It works with R.
yes, but you need an M+ version installed in your local desktop.
Yeah,
Mm.
so you'd have to run R on the virtual desktop with M+ to get them to talk to each other. But what that does is it helps you write the syntax, and then you can have M+ run it, and then it brings the M+ output back and into R objects. So then you can do stuff like make tables and do all the R things. So that makes it a little better. I have not played with that a lot, but it seems like a very useful idea. So that's why, like, this is a script. Like, this is the entire file that has all the information about the data, the variables, the analysis choices, and then the model itself. So things in blue are dedicated commands. They will appear in blue. Things in green are comments. And here's a new one, exclamation point. That's your commenter. Yeah.
Actually, I like that. Read this.
Yeah. Yep, so that's why it's in green. Anything in black is something that you would change as well. So the data set, M+ only works with text data. CSV is what I would recommend because you can usually open that up in Excel and make sure it looks okay, but DAT is also an alternative. And you can do fixed format data or free format. I would strongly encourage free because fixed is painful. That's the one where you have to say how many columns each variable is, like 4 at this, 3 at this, do that. It takes forever. Names, this is where you tell it what the names of your variables are. They're not in your data set. So that means, practically speaking, you would want to limit your data set to just the stuff you're going to use. Otherwise, you'd have to write this out, and it would be huge. And each of these names can only be 8 characters at most. It's like 1985 in here. Use variables says which ones are going to go into your model. Otherwise, it tries to put everything in your data set into your model. Missing data code tells it what values to ignore. Then analysis. I'm going to use maximum likelihood. Type equals general is the default. That's what you'll do for most things. I would like some confidence intervals, a standardized solution, the residuals by which to look at misfit, and modification indices. Yep.
Question or comment. The reason that you have -999 is your own personal convention from when you created the blanks you filled in, yes?
Yep. So pick a number that is not likely to be a real value for any variable. That's my logic here. So -999 in the context of what I'm doing would never happen.
Okay.
If you forget it, or
Will the model think that it means zero or negative?
if you don't tell it in the instructions, yeah, it will be treated as a real number. Yeah,
That could make an impact.
it will make a very bad impact. And you will know right away when you look at your output and you're like, how do I have a mean of negative 70 on a scale from 1 to 5? True story. When I first started teaching, I let students use their own data for stuff. And I got a table of descriptive statistics for a variable where the minimum was minus 99999. And I was like, ugh. Like everything after this is wrong now because you didn't realize that you had missing data that you didn't flag. So, good times, right?
Mm-hmm, clean
Yeah.
your data.
Yeah, well, well, at least descriptives can tell you if that is a
Yes.
problem. What's your minimum, what's your maximum, and what should it be based on your data? That's the thing. All right, 309. We're almost going to get through this. So 3 things you need to know about M+. If you see a variable listed all by itself, just the name, that refers to a variance of some kind for it. Either residual variance if it's being predicted, or just straight up variance if it's not. Stars refer to the idea that this is estimated. You can type them or not. I put them in there to be explicit. With means covariance. So this one line of code, by listing the same outcomes on both sides of the with, gives me all possible covariances. It's more efficient.
Like making a matrix, so to speak.
Exactly. The off diagonals of the matrix. Yeah, so the diagonal would be here, the off
Yeah,
diagonals
right.
would be here. Things in brackets are either intercepts or means. And it knows which it is. It's an intercept if it's a variable that's being predicted. It's a mean if it's not. Last but not least, the word on. That comes from old school way of talking about regression as regress y on x, which is never ever how I say it because it sounds backwards to me. The way that you can make this make sense to you is to visualize, rather than the word on, that it's an equal sign. Then it looks like an equation. Y equals these predictors. So on is the magic keyword for that. So this is 2 predictors of 1 outcome. This is 1 predictor of 3 outcomes, and you can stack them up on both sides. So you can fit as many regressions as you want to on one line of code. However, it becomes tricky to figure out which labels go with which, and so that's why I separated out this one, because I knew I wanted to label these things. And it works the same way as Lavon, in that these labels refer to what these slopes are going to be, and then I can do math on them down here by defining new terms that are the result of the math. So like this one, for instance, is the difference between the slope of dad's education predicting the kid versus the mom. So linear combinations in M+ also possible for anything, not just fixed effects. Hooray! So we have the same information structured differently in M+ about our fit. Number of free parameters means the number of things we estimated. Here is our chi-square test. The test statistic is 10. 6 things we left out of the model, and that is not significant, but a little too close for comfort. Up here are the log likelihood heights. We are the HO. Your model is HO. The best possible saturated model is H1. So what's happening is that it is doing -2 times the difference between these 2 things right here for you. So it's testing your fit for you. You don't have to do that. Then the rest of them, RMSEA should be low, that's a little on the high side. CFI should be big, that's a little on the low side. SRMR is reasonably okay. Then the output is structured similarly, but it does an ordering that it decided on. So slopes first, covariances second, and then intercepts and variances last.
And that's why the ons are with versus are with, and that's how we can tell our difference.
Yeah, if it's an on, it's a directed slope. If it's a with, it's an undirected covariance. And it's estimate in the first column, standard error. Estimate over standard error, we used to call Z or T, depending on what class you're in. It labels it this way. And then a 2-tailed p-value. And this is me trying to help you map which slopes go with which slopes in the equations. Ta-da. And then these are the slope differences I asked for under the new section. All right. Question from the Zoomers here. Would I recommend using Stata or R or M+ based on whether or not we want to take multi-level models in the fall? Would it be better prepare us to use the latter? I would say for immediate purposes, using Stata or R, if that's what you've been doing all semester, is fine. If you know for a fact that you want to take structural equation modeling at some point and you'd like to have M+ at least a little bit familiar for that, you can add it. But if you're like, no, I don't need one new thing in my life right now, that's fine. M+ will not be used in the clustered class until the very, very end, and that will actually be multi-level structural equation modeling, has different code and different conventions in that as well.
Will M+ for us be terminated at the end of the semester since it was only associated for us to have it because of this course?
To the best of my knowledge, no. You will have access to it so long as you are a registered student, once you're given access. But I have to feed a list of names to people manually to make that happen.
Because my thought was, well, if we don't do it now, well, if we still have access to it like in the summer.
Yeah, you could play with it later.
Play with it later.
Yes, I believe that to be true, unless they've changed something.
Rules change.
Yeah. So yeah, you don't have to use M+, but if you know that in like your research, like, because hopefully this is not just about getting through this class, it's about using this stuff to do things. Like Lavon doesn't have any link functions besides binary and ordinal. So that's all you can do in Lavon. Stata's GSEM has the most, second to M+ has fewer, but still quite a few. So M+ has count models in it. It has nominal, it has binary, it has ordinal. So it covers most of what we've talked about. It doesn't have binomial and it doesn't have like gamma, but you can do log normal with it as well. So if you know that you're going to have generalized outcomes in your path models, I would recommend either GSEM in Stata or M+. GSEM doesn't do as good a job with missing data as M+ does though. So it's like, there's always a trade-off. Happy to chat with anyone individually about what would be most optimal given your specific types of data and needs and stuff. All right, 3:16. That means we got to go.
We got bonus.
I know, bonus minute. Like, we're just late. All right, let's see. It's Thursday, which means I say have a good weekend. Let us know if you need anything. I'll let you know when your homeworks are graded, and I hope to see folks back here next week for our last week together. All right, bye for now. Bye, Zoomers.